Good morning, everybody, and welcome to this new, this webinar from the National Federation of Engineers for Electrical Safety. Today, we have a very interesting subject. We're going to be speaking about earthing and bonding of information communication technology systems. So this is a very relevant subject for a lot of us who are working with uh, data centers, any sort of equipment that involves computerized equipment, basically, any sort of areas that electrical installations that involve computerized equipment. So, yes, we are the National Federation of Engineers for Electrical Safety. We're a registered not-for-profit society in Tamil Nadu. Um, Our mission is to create awareness for electrical safety. We want to make every electrical installation free from accidents. This could be electrocutions, fire, or short circuits. And we also would like to increase the reliability of it. You can visit our website is nfees.org. Yes, we're also fighting for a much better tomorrow. Currently, there are several accidents that occur, leading to not only deaths and injuries, but even loss of property. Uh, Our vision is to make, like I said, every electrical installation free of accidents, that is electrocutions and fire short circuits. We also want to increase the reliability and contributing to the saving of life, property, and of course, supporting sustainable development. You can't have sustainable development, and sustainability is a big buzzword for now if your installations keep burning to the ground. We shall strive, some mission, we shall strive to achieve our vision through getting accredited for product and personal certification, which shall focus on electrical safety by design, manufacturing, installation, and maintenance of electrical products, and installation by competent and qualified manpower using quality resources, including product, processes, and procedures. As you all know, we're also working on the new scheme, which is the personal certification scheme. This is mainly to do with this. What we do is we create awareness on electrical safety. One of these webinars is obviously a prime example of that, as well as the events that we're doing in almost every, trying to reach every city in the country. To improve skills of practicing electrical engineers, also improve the safety measures followed in the industry, very important as well, and to introduce some modern safety measures in engineering and to generally improve the quality of electrical installations. There are a variety of membership options. As you can see, more information will be on the website. Membership is at a very nominal cost for an individual of only INR 1,000, for a corporate only INR 5,000, and for a MSME only INR 2,005, 5,000. Yeah, sorry, that's 500, 10,000 and 5,000. Okay, so we've done a lot of webinars, of course, previously. Earth Electrodes, this is one of our events at Nagpur. This is for Earth fault impedance, very hot topic. CEA regulations, of course. Another event in Vadodara. We've done a lot of events. They're just a couple. Power quality, harmonic distortion. We have a WhatsApp group as well. A lot of discussions happen on it. You get access to it as a member. Power quality is one of those hot topics there. Another event in Chennai. This was about some time ago. Channel discussions of our members as well on power quality again. Mitigation is relevant to power quality again. Solar PV installations, very interesting subject on large scale solar PV installations. Green wire, of course, with our sponsor Polycab. The previous webinar, which was done with Nandu on system earthing and fault protection in prosumers electrical installations. Very interesting subject, of course, because now we have a new concept of system referencing conductors and how that changes with varying system earthing. Power system earthing is quite interesting. Electrical fires in hospitals, again, very, very relevant subject given the current occurrences of fires. Also done this. And of course, today, just before I get into today, all of these webinars are recorded and available on the website, unless they were paid ones, of course. They're available on the YouTube channel. So today, functional learning and information communication technology. So I'm your host. This is not about me. So I'll just skip to our subject speaker, Mr. Nandu Gopan. So Anandu is a graduated engineer in electrical and electronics engineering. His expertise is EMI and EMC design for buildings. So that's electromagnetic interference and electromagnetic compatibility. Also, transient analysis and interference studies. He's also currently pursuing a master's research on electromagnetic shielding in aircraft. That's quite interesting, I think. Obviously, a member of the BI, of the Bureau of Indian Standards or ETD 20, Electrical Installation Sectoral Committee, perhaps one of the most important BIS committees in this field. 30 surge arresters, again, related, very relevant. 50, of course, LVDC, very interesting as well. It's a little new stuff coming up in the electrical installation space. MT3 for TC64 and which is for electrical installations, and MT3 and MT8 for TC81. I believe that's for lightning protection and associated products. He's also uh, done a lot of these events, presented a paper at the International Conference on Lightning, Electromagnetic, and Semiconducting Materials. He also presented a paper at the 17th International Fire Conference, and he also published an article titled Casualties Due to Fire in Air Conditioners. This is a very interesting article given the, and also very relevant given the amount of fires happening right now. Anyways, that's enough from me. I'm going to hand over to Anandu. This it's all yours.
Thank you, Krish. Thank you for the nice introduction. Can you unshare the screen? I will start sharing it.
Absolutely. One moment.
Sure. Okay. Wait, I can think. Yeah. Yes. Let me just share my screen. Okay. I hope the screen is visible and there's no issue in this.
All good.
Yes. Thank you. So, gentlemen, our topic is telecommunication. What type of earthing and bonding you're supposed to follow in it, building with telecommunication, basically with modern computing, hospitals, industries, automation industries, data centers, basically those kind of installations. So standards which basically guide these installations is you have an ISO IEC standard, which is ISO IEC 30129, basically for telecommunication buildings, any building with any telecommunication equipment, example office building, even residential building, you have your data centers, hospitals. This standard comes into play. It is ISO IC. And then you have your ITA 607B. ITA, it's a very famous standard for data center. On This talks about how do you do the bonding in uh, data centers. And basically, these two standards, sorry, one second. These two standards join and form this standard. Actually, no. If I have to clear this standard, ITU K27, this standard is replicated in ITA 607B and ISO IC 30129. So basically, you can see references of ITU K27 in both of these standards. And if you want to go through on how this standard is formed, you have to refer to ITU K27. And all of the references you can see in many parts. In when you come to specific clauses, it will tell you to refer ITU K27, both of these standards. And then you have your IEC 61340 part 1, which talks, it is a general standard on how to protect your electronic devices from electrostatic discharge, ESD. So basically, after this comes, all of these, PP standards for electrostatic protected regions. And then we have, so today's webinar will be on these four standards, a combined of these four standards. And then at the end of the day, the goal of this webinar or of all of these standards is to minimize the risk of operation of equipment due to electrical hazards. Basically, if you have any electrical hazards, maybe EMI, EMC, how do you not? How do you make sure that there is no damage to your electronics telecommunication equipment? And this is also to provide a very reliable signal reference path, and also to improve the immunity of against EMI. Finally, all of this standard, when you follow it perfectly, you can also be protected from ESD, that is electrostatic discharge. So applicable locations are these locations with modern computing, which I already repeated. So example, it can be a control room, the aircraft control room, can be your data center, server rooms, hospitals. In OTs, you are supposed to follow something different, but in the OTs also, when you have your equipments, you can use this kind of bonding to connect these life-saving equipments also. And you have your audio visuals and security rooms. In hospitals, you are supposed to add few more uh, restrictions. So obviously, that is not covered in this webinar. It was covered previously in some few other webinars. There was a webinar on medical locations, and then different types of earthing. So basically, uh, there's this general symbol for earthing. Generally, this is a very generic symbol, 5017. So this is just to say that connection to this point has to be you have to connect an earth to this point. It's a very generic symbol. Or connecting to this point, it's considered as an reference potential at that place. And then you have your functional earthing, you have your protective earthing, you have your chases and equipotentiality. So you can find your one second. You can find your protective earthing in in your P in your electrical installation. Your P, that will be your protective earthing. You will have your MET. That all of those are protective earthing. Basically, earth which is used for the safety, it is called as protective earthing. And functional earthing, it is for earth which is provided for signal reference path, basically to provide uh, a reliable signal reference path between two communicating equipments. And then you have your chases earthing. You can find it in IS 3043 for your generators. You are supposed to connect the generators to chases. And then you have your equipotentiality. Basically, connect. If you find it in an equipment, it means that connecting this, you have to connect it to a part where all the surrounding equipments are at an equipotential plane. And then you have this is just some kind of examples on different. You can find these symbols. Basically, this is for functional earthing. Functional earthing. You can find your P. This is your P protective earth with functional earth. This is your functional earth. So basically, different kinds of pictures, examples for you to know that there are uh, functional earth and protective earth is not the same. There are some restrictions which apply to functional earth, and it cannot be readily be connected to protective earth also. Next, coming to our subject, that is our telecommunication buildings with telecommunication equipments. So, what is the requirement for power distribution and for against shock protection? What is the general requirements? So the best system you can go for is TNS system. You have your separate metallic fault return path from your equipment to the source. And then in case you are using a TNC distributed supply, at the commencement of supply, you have to change it to TNS. So it will be kind of like a TNCS. But using TNC inside your building is strictly prohibited. You are not supposed to use it. And then you have your TT and IT. If you are going to use TT or IT, the PE conductor, you can derive it from the MET obviously. And this PE conductor sizing must be as per TNS system. And then it's recommended to have your own transformer and convert it into a again into a TNS, because TNS is you have a separate fault return path. And then this is for the AC side. When you come to DC side, generally you have two kinds of system. I'm not talking about the DC side TNS, TNCS or anything like that. You can go with the TNS itself. But when you come for the DC side, you have your positive and negative, right? So when you have your positive and negative or your midpoint, there are two things which come into play. Either you can earth it uh, single time, which is called as isolated earthing, or you can earth it multiple times, which is called as multiple earthing. You can only earth your positive side, not your negative side. This positive side, you can earth it either multiple times or a single time. If you are doing a single time earthing, it is called as isolated. Generally, the how it is represented is DCI. This I means it's either isolated or it is DCC, which is common multiplied, commonly earthed. And then you have a BN. What type of bonding network you are following? So anyway, we will this BN we will get to it in the further webinar. So there are different kinds of BN bonding networks, which I will go through it after some time. And then the best is you have to design this as per IC 60364 or your IS 732, which is right now mandatory requirement in India. One more thing is, if you have your multiple DC, multiple connected DCN and isolated DC, how are you supposed to choose between these two things? You see, when you have a multiple connected DC in your positive side, you're having multiple connection to Earth. You see, this will result in you can this cross section, right? You can use it for higher current, and the temperature will be less, and the voltage drop will also be reduced uh, because of because the mutual impedances are low. The even these the conductor impedance will be low when you use a multiply connected bonding network for a DC, and when you use an isolated DC system, that is basically one time connection to the earth. The positive side is one time connected. So in this, you can use it if your load is more than one electronic system. That is basically you have your battery or whatever, you have your converter battery, and it is going to multiple electronic system throughout the entire facility. Then you can go for a DCI. If not, you can go for a DCC. And then this load, whatever your electronic system is, it is also very sensitive to the transients which occur due to some short circuits. Basically, when there's a short circuit, the area around that place, it is very sensitive. There will be a lot of EMI, EMC. So basically, if you have loads with these kind of system, you can go for a DCI or you can go for a DCC. Now, this will be how your telecommunication building will look like, maybe in a rough diagram. So basically, you have your building, you have your MET, you have your this will be your PBB, which I will get to it after some slides. And then you can see different regions in the sense you have your this is one region with some equipments. This is the equipment, and likewise, there are multiple regions. So best thing you have to do is you have to classify your entire entire building or your installation into these kind of regions, like regions where there are some telecommunication equipments. Obviously, it will not be everywhere. Data racks will not be everywhere. It will be in either one room. maybe throughout in some locations. So you classify these locations as locations with telecommunication equipment, areas of telecommunication equipment distribution, and then you what you are supposed to do in these regions is what is defined right here, and how you are supposed to interconnect between these regions and what are the requirements. So basically, you can see that there are some connections, and uh, if you are going to use an optic fiber communication as the optic fiber as your cabling medium, then the sensitivity of uh, that system is very low, because optic fiber you have no EMI/MC concerns. So there is no issue. If you are going for an optic fiber, you can also ignore the bonding network performance also. But obviously the price is expensive. Next one which comes is the symmetric and asymmetric cabling. Basically, symmetric is for balanced application. So, screened or unscreened cables with balanced application. The sensitivity of this bonding network will kind of be little bit okay. It will be in the medium range. And if you are having unbalanced applications, your your requirement in your bonding network, that is for your telecommunication bonding network, will be much more stringent. You have to, it will be much more dense. Basically, best thing you can go for is go for a balanced application. Your load is everything is balanced, and try to avoid any unbalanced applications. So if you are going to connect your protective earth to your, if you are going to use any protective earth, or you are going to connect your telecommunication, at the end you have to connect to the protective earth. What is the requirement of this protective earth? So in the previous slide, you can see these are some zones. This is zone one, this is zone two, or this is zone one, zone two, and between these zones there is one connections. Yes, one second. So between these zones, what you are supposed to achieve is an electrical resistance of 2.5 milliohm per meter. So within any of your zones inside a telecommunication building, you are supposed to achieve this resistance. Basically, all of these METs are interconnected such that they will at least achieve 2.5 milliohms per meter. That is the minimum requirement for an electrical when you are going to connect your telecommunication building to a electrical network. Basic, and this is DC resistance. You don't need, we don't need to be worried about the high frequency impedance and all. So just this is DC resistance, and you can avoid it. If you cannot achieve this value, you have to go for a mesh bonding system, which we will come to it a little bit later. If you're going for a mesh bonding system, you can uh, avoid these requirements. And again, when you are going to use a telecommunication bonding network without mesh bonding system, if you're not going to use any mesh bonding system, just a plain telecommunication bonding network, uh, you have things called as PBB, which is primary bonding bus bar. You have secondary bonding bus bar, and interconnection between all of these points. Basically, in your server room, you will have your racks, cabinets, and all of those things. When you are going to connect, you have to reach a resistance of 1.67 milliohms per meter. And I will tell you how you are supposed to interconnect all of these things in the upcoming slides. In the upcoming slides, all of these are clearly mentioned how you are supposed to interconnect. What is PBB? What is SPB? I will explain it in the upcoming slides. So, general requirements: any telecommunication building, you should have your own telecommunication entrance facility. Basically, the place where all of these telecommunication network related things are entering your facility, and you should have an MET to basically connect all the extraneous and metallic parts in that region to the MET. So it is a requirement to at least have one MET at that region. That region is called as TEF, telecommunication entrance facility. So basically, this is to limit the surge, into the building. Basically, if you see your lightning protection standard also, each and every zone will have an surge protective device. So to control the surges which is going into the other zone. So basically, at the entrance, you have to have an MET, and you are going to reduce the surges entering your building. Maybe you can use an SPD, you can use your data SPDs, all of these things to interconnect. These systems, it can be cables, armoring of these signal cables, even power cable armoring, and it can be anything. So and then you have your common requirements for these in the upcoming slides. Whatever I'm going to explain, these common requirement apply regardless of the application. So what I'm explaining, it's preferably it can be a copper of 95 percentage IACS, which is basically International Annulled Copper Standard. It should have at least that much conductivity. And then all of this joins, which I'm speaking in the upcoming slides, it must have at least less than 0.1 milliohm contact resistance. Basically, the contact resistance between two joining equipment, two joining conductors or some plates or bus bars must have at least 0.1 milliohms, that is 100 micro ohms. And the mating surface of these bonding components, basically the surface of these bonding components, they should have an electrochemical potential of at least less than 300 millivolt. Basically, it is preferable if these two are the same material, you don't have to be worried. If they are of these different materials, you have to follow these two conditions. And as I've repeated again, this installation, it must be as per IS 732, because no matter what type of telecommunication requirement you have, what is important is safety. Only after that comes the requirement for telecommunication networks. And then if you are going to do with, you see in the upcoming slides, I will tell that you have to connect this part, there'll be some multiple connections. And these connections, it is preferable that if they are at least 150 millimeters away. Basically, if you are working in that region, you will not disconnect one of these conductors, during maintenance. To avoid that, you should have at least 150 mm. And in places you cannot have it, it's better to follow this 150 mm minimum requirement. And multiple bonding to a single bonding point is also not allowed, because during maintenance you can remove this, and your entire electrical system will be at jeopardy. So it should not be to a single bonding point. You can have multiple bonding points with 150 mm separation distance. And these bonding conductors, it should not be placed in a metallic conduit. If it is going to be placed in a metallic conduit, you have to bond these two, the end of the metallic conduit, basically the ends of the metallic conduit to the bonding points. So first, you have your racks, server racks, data racks. Basically it's the same, and you have your equipments. So for these equipments, you have something called as an RBC. Basically, what it means is a rack bonding conductor. You are going to connect all the metallic parts in your rack to a single conductor, or a single bar, and you are going to take it outside. And this, when you take it outside, you'll go and connect to another point, which I'll explain it in the upcoming slides. The most important thing is, when you are having such a connection from this metallic point to this, one second, from this metallic point to this, either this or this, or to this bar. These two are bars, and this is a conductor. Whatever connections you are going to follow, This should not be looped, such as it should not go like this, and then you are taking it outside. This is not allowed. You are supposed to individually earth them. Yes, it should be individually earthed. You can also see here, this is already, all of these are individually earthed. Here it is individually earthed like this. You are not supposed to loop them. Basically, what happens when you loop is, if you have an leakage current or some problem in this place, this leakage current, if you loop them, it will go to this place and then it will go to this place. Basically, it will cause issues in other equipments. So you are only supposed to individually earth them, and it must not be uh, looped. One second. Okay. And these conductors, they must be easily detachable for maintenance purpose also. So if you want to remove one of these rack, it should be easily disconnectable. So for EMI EMC concerns, it is better to connect these the cabinet doors, panels, the cable organizers, all of these things to a common place, such as this equipment body itself, or it will be the RBC. In the previous slide, you saw this RBC, right? Rack bonding conductor or rack bonding bus bar. And these parts, actually, you can see that in this, you can see this interesting thing over here. Basically, it is to disconnect. So if you want to remove any of the parts, you can disconnect. Do not remove this. Remove this, and you can easily work with your things. If your equipment is welded, the body is welded, you don't need to be worried about this. And then you have your telecommunication bonding network. So this is basically, if you are going to follow a mesh bonding network, this is not required. Bonding network has a different set of requirements. And if you are going to follow this telecommunication bonding network, in the previous slide, I showed this requirement, right? You are supposed to follow this as well as this requirement to have a telecommunication bonding network. So basically, in a telecommunication bonding network, what you will be having is a PBB, which is basically this thing, and you will have your SBB. This is your secondary bonding bus bar. You will have your primary bonding bus bar, and then you will have your interconnection between these primary bonding bus bar and secondary bonding bus bars. And these secondary bonding bus bar and primary bonding bus bar, they'll be interconnected with that zone. So basically, SBB will be interconnected to one BBB, and this interconnection between these conductors, we will generally call it as backbone conductors. Basically, to interconnect between SBBs and all, you will call it as telecommunication bonding backbone. And if you're going to connect from TBB to MET, you will call it as TPC, telecommunication bonding conductor. And one of the main requirement, okay, this is for a large building. You have multiple, maybe you have multiple zones, and all of these zones you have your SBB, and you're coming to and connecting to an MET. Or you can or maybe this can be one floor, and another floor you can have a similar setup, like likewise. And if for a small building, only this is required. This PBB can be connected to all your cabinets, the equipments in the telecommunication room. And basically, when you are going to have two different PBBs, that is your primary bonding bus bar in an electrical installation, you are not supposed to connect between two primary bonding bus bars. And it's it's good you don't connect it, because there can be some circulating currents if there are going to be leakages. So you are isolating between one telecommunication bonding network and another telecommunication bonding network unless they are communicating. And then you have your SBBs. Basically, SBBs, they are also not supposed to be connected to. other SBBs of other PBBs. You get it, right? So you have in your one floor, you have your this type of interconnection, and another floor you have again this type of interconnection. You are not supposed to connect this PBB and the next floor's PBB. If you are going to connect, you have to follow this dimensioning rule, this dimensioning rules. So unless it is safe to do so, you are not supposed to connect all of these together. And uh, uh, even the first floor, suppose this is first floor, even this SBB should not be connected to the upper floor SBBs also. If you are going to connect, you have to follow those the requirements. You know, this SBB and PBB, what and all will be connected is your TBC, your TBB, you have your RCB. Your RCB is your rack bonding conductors. You have your structural metals. You will have your local SPDs. An SPD of this locations can be directly connected to this bonding bus bars, and the structural metal at that location, preferably you connect it to the structural metal also, and the bus bar sizes of this PBB and SBB. So PBB is primary bonding, so it is a little bit more bigger. This is 100 mm, minimum 100 mm, and this is minimum 50 mm. The thickness is 16.35 mm, and the contact resistance when you are connecting to this bus bar must be less than 0.1 milliohms, 100 microohms again. And this, if it is the same metal, no issues of electrochemical potential between these two surfaces. If it is going to be separate surfaces, different materials for these surfaces, it should have at least 0.300 millivolt. It should be less than 300 millivolt. And then the crimps which are you are going to be using at these locations will look somewhat like this. There are different sizes of these crimps, and these crimps are 2 volt lugs, and you are supposed to connect to both of these. It will be connected to both of these. And again, you have your telecommunication network. You are going to use it with when you have your telecommunication equipment. Obviously, you will need some power requirements, right? So when you have power requirement, you will have your protective bonding network. That is your PE conductor. You have your MET. You have your equipotential bonding and all of those things. So when you have such a requirement, when you have protective bonding network, basically you can consider this as one of your panel, and this is your secondary, maybe a downstream or downstream panel or your upstream panel. Two panels which are interconnected through a PBNC. PBNC is nothing but protective bonding network conductor, which is basically your PE conductor, protective earth conductor. So when you have these two conductors connected between the METs of this panel and this panel, of panel 1 and panel 2, preferably you also connected to the structural shield, structural steel, electrically continuous steel, so that the EMI generated due to some or due to some maybe uh, short circuit or some fault can be reduced through some current flowing through the continuous structural steel also. This steel must be an electrically continuous one. So you have to make sure that this is electrically continuous. And in the upcoming slides, I will be explaining about TMI AMC and how you can prevent through this kind of network. Basically, when you connect all of this, like to the structural steel, and when you connect your telecommunication also to the structural steel, you will follow a mesh bonding network, which is coming in the upcoming slides. So again, so you have your telecommunication, bonding network, and you have your power. You have your power requirement. So this is basically the PE conductor, which is going to an MET, and the MET is connected to other METs or however it is connected. So This is your, maybe you can consider this as one of the distributed cable. It can be your power cable or your telecommunication cable, whatever. And inside these two, you have your signal cables. So, signal cable between equipment one and equipment two. So when you have such a connections, if you have a electromagnetic field which is from some transient occurring outside, or maybe even 1 kilometer away from this system, how it will affect this? This will follow this will form a large signal loop. When you have such a large signal loop, the current induced in this loop will also be larger. You can face some failures inside these equipments. And in the next slide, I will be explaining about system interactive over voltages. Basically, when you have a SPD and it works, what will happen to your cablings? So to avoid these kind of large loop is a huge problem, and it must be controlled in any telecommunication buildings with telecommunication equipments. So how you can control is, you have your secondary P conductor or some backbone conductor. You connect the equipment body one and equipment body two. So this EMI field, it will occur only between the bodies of this part, which will basically not affect anything. This conductor is connected to the internal equipments, and this loop is small, so there will not be much induced currents in this loop. So in these locations, you will require supplementary bonding, and you will have to use a lot of conductors to interconnect. It will become a hassle. It will become a headache to interconnect and how to reduce EMI effects in a telecommunication bonding network. And another interesting subject called a system interaction over voltage. Basically, in your equipment, or if you have your house or something, you have your electrical installation, right? So basically, your electrical, you have your house and you have your electrical installation. Basically, this is your equipment, and you have your electrical service, and you have your communicating service. So I'm considering the worst possible scenario, that is, these two are coming from the opposite ends of your equipment. And preferably in your telecommunication building, you have it, all of these entrance, you have it at a one location, with obviously with the minimum distance. As per IS 732, you are supposed to follow some minimum distances. You have to follow that minimum separation distance, but preferably they can come through one location, not through two different locations. So you have your equipment, you have your SPD, and this is your incoming SPD or your telecommunication SPD. Basically, your network provider will provide it to protect his telecommunication lines. So suppose I am having a I'm having a surge. Yes, I'm having a surge coming through your communication service lines. Obviously, your SPDs at this region will divert your surge to your P, and this is your equipotential connection. It can either be a P conductor or your MET, whatever is connected, and this will be connected to a common point, right? Where your electrical installation is also be connected. So the issue is, you can see that there's a huge current flowing through this conductor, and this part will form a loop. Basically, this is connected, the earth is connected to the equipment body, and telecommunication service line, which is obviously going inside your equipment to some for the communication requirements. So there'll be some port here, right? Port 1 and port 2. I'll just mark it. You have a port 1 and port 2. So what happens is, there'll be a potential difference between the body due to this uh, due to the loop, right? Due to the loop, there will be a potential difference between the body and the telecommunication port 1 or port 2. There will be some potential difference. This is an open voltage circuit, so there will be some potential difference between these two uh, parts, basically the port and the connection point, which will be insulated, and the equipment body. What happens is, if if your equipment is not rated properly, or if there is a huge surge which is incoming through your communication service line, this this part will face an insulation failure. Basically, there will be a spark over from the port to the earth. So you have to avoid these kind of interactions, to avoid these kind of potential difference even when an SPD is working. So to avoid these kind of interactions, you have to follow a strict EMI you know, EMI protected system. That is why in the previous one I told that you have to interconnect a lot of system to avoid these loops. Basically, again, it becomes a hassle. Or to avoid these kind of interactions, you can go for a mesh bonding network. Yes. So basically, due to the voltage drop and the and due to the voltage drop, there'll be a loop formed between this, and there can be a spark over. That the voltage, the insulation will be stressed at that point. So you have a mesh bonded network. Till now, I'm telling, if you have your mesh bonding system, you don't need to consider this. If you have your mesh bonding system, you don't need to consider this. What is this mesh bonding system? So mesh bonding system, when you're going to follow, I will list out the requirements of mesh bonding system. Yes. If you're going to follow a mesh bonding system, the DC resistance of this grid to adjacent points must be less than 1 milliohms. It's a very demanding requirement. And then when you have your inductance, a grid can also form an inductance when there is some current flowing through it. So the inductance must also be less than 6 microhenry, which is a very small value. You are supposed to measure these values after you install a mesh bonding network. In fact, all of these requirement which I told, the 1.67 milliohms per meter, you are supposed to uh, test it. You are supposed to test it, the continuity after an installation. And then they should be bonded with the protective bonding network. And then they can be when you're going to implement a mesh bonding network, these will be connected to your structural steel. So there is a risk of lightning effects, lightning damages. So you have to follow IC 62305 part 4. Not the part 3 is for protection against building, damages to buildings and health, maybe human life. That is part 3. Part 3 is for purely for building protection, for the damages, physical damage to the building and for human safety. Part 4 is for protection to building against these this is for electronics and electrical equipments. If you want to protect your electronics and electrical equipments, you have to follow the part 4 of ISIEC 62305. Part 4 is more stringent than part 3. You'll have a lot of design requirements such as shielding, bonding, SPD requirements, equipotentiality. Those requirements will be covered only in part 4. So when you're going to follow a mesh bonding system, it must be the DC resistance between two adjacent points in a grid must be less than 1 milliohm. The inductance must be less than 6 microhenry. It should be connected to the protective bonding network, and it must be as per part 4 of 62305. So before I go into mesh bonding system and isolated mesh bonding system, I will just give an definition. This is as per ITU K27, what the general terms which you will use in a mesh bonding system. So you have your common bonding network. Common bonding network is nothing but, effective bonding and earthing inside a telecommunication building. So basically, you have your metallic components, you have your intentionally or incidentally interconnected. These, all your all your metallic components are connected. It can be interconnected, it can be looped. In some places, you are not supposed to loop. So basically, they are connected to form a bonding network or in this region. So basically, every metallic components must be bonded. This component can include structural steel or reinforcing rods. You will have your metallic plumbing. If you have your plastic plumbing, no issues. If you have your AC power conduit, obviously you will be having it. You will have your metallic conduits. You are supposed to interconnect them. You will have your PE conductor, which you are supposed to interconnect them. You will have your cable racks, bonding conductor, telecommunication bonding conductors, which you are supposed to interconnect. Yes, this will form a common bonding network. This is generally called as common bonding network. Basically, you are connecting whatever dead metallic things you find in your in your building to you are interconnecting all of these dead metallic equipment, dead metallic parts. So, in common bonding network, again, you will have interconnection for your telecommunication equipments. You will have mesh bonding network and isolated bonding network. This is isolated and this is mesh bonding network. So, mesh bonding network, I'll just read the definitions. Basically, mesh bonding network is for, a bonding network in which all associated equipment, frame, racks, cabinets, and usually DC power return path, that is your positive, are bonded together at multiple points to the CBN, and they will form a mesh bonding network. Basically, I talked about RBC, right? Rack bonding conductor. In this rack bonding conductor, you will be connecting your cabinets, you will be connecting your rack metallic things. All of these dead metallic parts, you are supposed to interconnect and fall, and you will form a mesh bonding network. And then you will have your isolated bonding network. Basically, isolated bonding network is just like mesh bonding network, but instead of this multiple points to your common bonding network, it will be one single point. You'll call it a single point connection. So if you are going, basically what happens is all your telecommunication will be bonded together. All your protective elements and your, your metal, cables, all of these things that is your AC power conduit, PE conductor, cable racks, bonding conductors, all of these will be connected together. So two system, which is basically your CBN and isolated bonding network, you will have only one single point connection. So that will be an isolated bonding network. In an isolated bonding network, only major requirement is when you're going to interconnect, it must be a single bonding, single point connection between CBN and IBN. And this, yes, this is a picture from ITUK 27. You can find some simplified pictures in TIA 607B, which is basically like you will find a very interconnected. You will find some meshes. You will find some interconnection between these mesh within the floors. Basically, this is a detailed diagram of how you are supposed to follow an mesh bonding network. So when it is going to be a mesh bonding system, again I repeat it, you have to connect your cabinets, cable racks uh, uh, to the system. It must be a TNS system, and the protective earth must be must be connected. All metal parts, dead metallic parts, you are supposed to interconnect. to the preferably to the MET and to the MET, and when you interconnect all the METs together, you will form a CBN, and the DC power return path along the conductor, you are supposed to earth it. So basically, in the starting of the this presentation, I told that DC you will have two things. One is called as multiple DC connections, and or you will have a single DC connection. So isolated DC connection. In this system, you are supposed to interconnect the DC return path along the conductor, along the DC return path. So you are supposed to do multiple interconnections. So basically, I will go through this picture a little bit. So this is your telecommunication equipment. So this is just a pictorial diagram of your telecommunication equipment. This can be one zone one with some telecommunication equipment. This is zone two, and you have no other telecommunication equipment. So basically, inside this region, you will form a mesh. This mesh sizing, basically, this mesh is to interconnect all of this um metallic parts or cabinets inside that build room. And major requirement is this mesh must have 1 milliohm resistance between two adjacent points. That is the major requirement in this mesh. There is no mesh sizing required, but you should achieve that 1 milliohm requirement between two adjacent points. So as long as you achieve this, you can mesh sizing can be anything. It can be 1 meter by 1 meter, 2 meter by 2 meter, 5 meter by 5 meter. Or if you cannot achieve, you will have to have a stricter. It must be much more strict. So at the end of the day, even after you design such a system, how you are going to install it matters a lot. If your installer, who is going to install such a system is not proper, such a system will never work out. And so mesh sizing depends on this 1 million requirement and the 6 uh, micro Henry requirement. Yes. And you can see that this conductor is your reinforcement. You are connecting your reinforcement to these places, or you can lay it along with your reinforcement. Basically, no change, but you should have some tap off points to connect to those points. And you can see that DC distribution, AC distribution. You have your lines and neutral and P. This P you are connecting with the mesh bonding system. Basically, you can see your TE which is coming and connecting to your ring conductor, and this ring is connected to your structural metal, and again it goes to floor. This can be floor one, this can be floor two. It is again in the floor two. Again, something like that is formed. All of the equipments are interconnected. You can see that this is inter-system cabling and interconnection of reinforcement and building steel. So basically, all of these are interconnected and connected to the reinforcement steel as well as to the bonding plane. That is your bonding mat. At the end of the day, you can see this is how your a typical diagram of your mesh bonding network. So you have your isolated bonding network. Isolated bonding network, you can see that even in the isolated bonding system, inside the grid, whatever equipments you are having, you are supposed to connect it. You are supposed to connect it to the grid. Yes. And this other equipments, uh, you see, there is only one single point connection to the reinforcement steel, and there is only one single point connection from the grid. This is a power cable. So, intra cabling requirement from one equipment to the other equipment. So basically, when you are going to do an isolated bonding network, this system has not should have one single point connection to the earth. So your telecommunication bonding requirement, it must have one single point connection, and it should be isolated from the reinforcement. So it should not be connected. It should not be laid along your with your reinforcement steel also. So It must be separate. So the problem is, even if you do an isolated bonding network, at the end of the day, some uh, special equipments will have, they will have a defined electromagnetic environment. Basically, if you refer IC 61004 425, I think so. Yeah. And a standard in IEC 61 4 part, some part, you can refer that each and every equipment is classified with an radiated field. So it can be class 1 to 5. So if your equipment is classified with this electromagnetic region, so you are supposed to follow a little bit more requirements. So such as you will have to form another, uh, one second. You are supposed to follow another supplementary bonding grid, or you have to have a system reference plane. Basically, you will have a more stringent grid to reach the requirement of this electromagnetic regions. These things can only be simulated. If you are going to calculate, you cannot calculate. You have to simulate it and see that whether you can, whether what will be the electromagnetic you know field at that region, and you have to define your system as per the electromagnetic field. Or you can have and you can have a transient suppression plate also. Basically, it is all your incoming power and signal lines will come through this plate, which will be interconnected with the reinforcement, and there will be an SPDs along this plate. So basically, this will reduce the lead length of this SPD, and there you can have an effective SPD, effective working of your SPDs. So this is how you do an isolated bonding network. Basically, you need an isolated bonding network only in places with uh, if you have a small system, maybe one room with some electronics, a server room, one room you have a server room, you can go for isolated bonding network. But for data centers, you're supposed to go for a mesh bonding network. Even in isolated bonding network, this grid spacing is based upon this 1 milliohm per 1 milliohm between two adjacent points, and 6 microhenry through the grid. Again, at the end of we are reaching the end. So I talked about telecommunication requirements for EMI EMC, what requirements you are supposed to follow. And now and for signal reference path, what is the requirement? That is your resistance requirements. And now finally to your ESD, that is electrostatic discharge, what you are supposed to follow. So if you want to protect your electrical and electronic parts against ESD, uh, the answer is very simple. You are supposed to interconnect all of these metallic parts, and the job will be done. But the problem is the human standing. He can be isolated. What can he do? He can use something called as an wrist strap, or there are special equipments or body wear, clothes, shoes, which are compliant to the standard. Basically, this is for as per IC 13912. I think so. Yeah, IC 13912. So basically, all of this will be interconnected, even your body, through some part, mainly through wrist straps, or some you'll have some clothes which can isolate you from an ESD phenomena. So when you are going to interconnect everything, they can be interconnected to your PE conductor, or it can be connected to your functional earthing conductor. But if you are going to connect to a functional earthing conductor, your functional earthing and PE conductor must have at least 25, must be less than 25 ohms, which it will basically fulfill the requirement. Every functional earthing conductor, at the end, it has to be connected to the PE through to the PE. So, and they will form less than 25 ohms requirement. Or you can also connect to a local equipotential bonding point. And then at the workplaces, you have something called as personal earthing, isolated parts, how you are supposed to handle. Personal earthing is your body, how you are going to, how the workman who is our working at that region, how is he going to be protected against the ESD. And you have your isolated parts, how it is going to be protected basically for your personal earthing. There are some footwears, example, there are some footwears or some there'll be some wrist, ESD protected wrist strap. So these will be connected to your protective earth or your equipotential bonding point. So these things, at the end of the day, all of this system together must have less than 0.1. Sorry, it must have less than 10 to the power 9 ohms. It must be less than this much ohms. And interconnection of all of these equipments will generally fulfill this requirement. And the maximum voltage generated in a body must not be more than 100 volt. Basically, due to electrostatic issues, your body can also generate some volt. Not generate, it is basically through the rubbing of your clothes. Uh, your body can be at a little bit higher potential. Basically, it will be it can differ. At the end of the day, you will get a shock, and then you will know that your body was at some other potential. So this body must not generate more than 100 volt to have this requirement. If you follow, less than this impedance requirement, it will be fulfilled. And then the products, that is your shoes, your straps, all of these must be as per relevant IEC 61340 part 4, and their compliance, all this requirement, the bonding requirement, you can verify them as per ICTS 61340 part 5 part 4 5 4, subpart is 4. And then part 4 is a huge standard which covers all your garments, your shoes, your straps. And then if you have an isolated part, basically conductors or anything which is isolated, and they cannot be connected to your PE or functional earthing or your equipotential bonding point, they must be, uh, if the electrostatic potential at that region can exceed 2 kV, you should at least place them 30 centimeter away from your, equipments which are prone to electrostatic discharge. So these insulated material must at least be 30 centimeter away. Better you can keep it 30 centimeter away, and you don't need to be worried. And then you have, if it is less than 125 volt, you can keep it 2.5 centimeter away from the equipment which is prone to ESD. And if you have any isolated conductors which cannot be earthed, so these conductors must have potential difference less than 35 volt. I'm not talking about your live conductors or anything like that. Isolated conductor, which is maybe for some electronic equipment, if you are maybe for some process, you are having such an isolated conductor which cannot be earthed. The potential difference between that isolated conductor and earth must be less than 35 volt. Strictly, I'm saying it again, it is not about the live conductors. And then if you have your access floors, which is access floors can also be used in mesh bonding network. You can use such a system in even in mesh bonding network, interconnect between these, between these stands. You can also follow a mesh bonding network through this also. And these must be connected to your cabinets or frames, PPBs or SBBs. So if you are having an access floor, especially to control your electrostatic discharge, their their minimum insulation resistance must be 1 mega ohm to your protective bonding network. 1 mega ohm to 10 mega ohms. Generally more than 1 mega ohms. So this is all for electrostatic discharge. And thank you. I think we can take some questions after this. Let me just.
Yeah,
Yes.
thank you, Nandu. That was really quite interesting, very different from what we generally discuss. But yeah, I think it was quite nice actually. Questions. We have one rather interesting question. I think that popped up earlier, but I think it's been answered. already. So let me just check the chat as well and see if there's anything. I know Mr. Apo has also joined in. He's talking. I think you. So Apo, can you are you
Yes,
audible? Yeah.
yes, Krish. Okay,
Okay.
okay. Thank you, Mr. Anand Gopan and Krish. It's a very nice and interesting subject. And a lot of new rules and process and methodologies are shown by Anand Gopan. It's a new learning, especially for the sensitive devices. So I would like to supplement only one point that as per class, what is EMI? As per class 3.6 of IEC slash TR 61000-3-6 2008, it is the electromagnetic compatibility is the ability of an equipment or system to function satisfactorily in its electromagnetic environment simultaneously without introducing intolerable electromagnetic disturbance to anything in that environment, which is very tricky. That is, it means the sensitive device should be capable of functioning in an electromagnetic environment. At the same time, it should not emit more EMI to affect the adjacent functioning devices. So with this, the measures are devised and explained very well by the speaker. For example, what I can say is, as a simple example, suppose if you have very sensitive device like ultrasonar in a hospital location, we can simply see what is the EMI, what is the EMC of that medical equipment. It should be observed as recommended by the manufacturer as per NEC. For example, I have seen one device. Whenever a mobile phone or a Bluetooth device are brought nearer to that equipment, it gets some wrong signal or wrong results. For example, any LAN or mobile phone may have an operating frequency of exceeding 100 megahertz. That means it's a radiating frequency. So for these such devices, you have to separate the equipment for all the equipotentiality as well as the interconnections and the minimizing the length of loop to achieve the equipotentiality. These are all of paramount importance in providing in achieving the compatibility, in achieving the proper functioning of the sensitive devices. It can be a conducted emission or radiated emission. Normally, radiated emission occurs above 30 megahertz and conducted emission is less than 30 megahertz. For example, VFD device or improper earthing arrangement in UPS installations, these are all radiated emissions that can be conducted through your distribution network. But radiated emission, it doesn't require any, it's only separation and mesh bonding as advised by Anand Gopan are more important. So it's a very tricky, however, it has been very well explained by the speaker. What I suggest, please, the participants, please go through this, all the standards referred by Anand Gopan to get yourself conversant with the mitigation that is required to achieve the proper functioning of all electronic sensitive devices and IT equipments. Thank you, Krish and Anand Gopan.
Thank you. I
Thank
think
you,
we have
Mr.
another
Thank you.
gentleman, Mr. Davies. Sorry, Ananda, were you saying something?
Yeah,
No,
Mr.
no.
Krish. Yeah, good morning. Am I audible?
Yes, yes.
Yeah, so thank you. I think it was one of the very good presentation on some new topic, telecommunication equipment and earthing. So Nam Gopal done a very good job and Krish moderating it. Now I have seen Appa have also come in the year. So I have a question basically. It is a bit of a practical question because when you enter into a electronic manufacturing facility, maybe a numerical relay, or where the requirement is that ESD, one has to wear the ESD shoes and that wrist what you are talking about. But here what happens that within that shop floor, you have 415-volt power supply. Now,
Yes.
this is a practical question, so maybe Appav sir can have some clarification. Here, what happens that when you wear the ESD shoes and enter into the shop floor, now you are supposed to enter with a safety shoe with electrically insulated. That is 15 kV safety shoe supposed to be wear. But that cannot be done in this particular environment. So, how one will take care of the safety wearing ESD devices like the safety shoes, wrist, and so on. Maybe Appav sir can clarify this, sir.
Yes, Mr. Davis, you are right. The electrostatic potential do exist in areas where you have complete insulation. Your shoes are insulated, the mat, the flooring is insulated. So it do occur, and it certainly electrostatic discharge is likely to happen. It will be in the order of kilo ohms. When you measure a person with reference to any adjacent metallic part, it will be in the order of say kilovolts. So the measures what you can have is the environment. For example, it gets aggravated during low humidity seasons. For example, if the humidity is far below 50 RS, then the ESD will be high. So that's why in textile areas and other things, they have electrostatic, the humidifiers. So if you see, you can see the same environment can cause electrostatic discharge during low humidity seasons. Another thing, electrostatic discharge should be done not a direct that shot from the person to the adjacent material. It should be electrostatic, since electrostatic is generated across the insulating part, the collection shall be insulated only. Then it shall be connected and equipotentiality should exist. It's not the effective earthing system. It shall be slightly diffused to have what I can say is there should not be a direct discharge of electrostatic discharge to the extraneous or earthing parts. It shall be collected through the insulating medium, then it can be discharged to the things. So ultimately what I can say is you have to make an environment that shall not create an electrostatic discharge. For example, humidification of the area or some of the thing you can deploy for the flooring. Flooring shall be neither highly insulative or totally conductive. It should be semi-conductive. So with these measures, we can minimize the electrostatic buildup. Then the efficient discharge, diffusing discharge can be the practical way of mitigating electrostatic potential to affect without affecting the equipment and the personnel.
Yeah. Thank you, sir. I just wanted to have little more clarification. So I'm giving a situation where there is a numerical relay assembly is happening. That means a very critical activity where the electrostatic discharge is very important and then component. So when somebody enter there as a person, the person can have up to 6 kV ESD at times. So what happens that the entry into the shop floor is restricted unless and until you wear the ESD safety shoes, which is conductive. Now, my question is that the electrician who is entering into the shop floor, he has to attend to some 415-volt motors there. Now, he is supposed to wear insulating shoes, but instead of that, he has to wear ESD shoes because of the environment. Now, under that, I mean, this is one question I came across in one of my audit in one of the electronic factory. So that's what I didn't have a proper answer to that. So I thought
Yes,
yeah.
you are right. It should not be an insulated. It is an anti-static. Anti-static shoe shall be neither conductive nor insulative. it shall be semi-conductive. It will be in the order of
Okay.
kilo ohms.
Okay.
So as I have already told, the discharge of ESD shall not be directly conductive or shall not be insulative. It should be a diffusing or a semi-conductive. So the first of all, we have to build an environment which shall not create an ESD. Secondly, the second measure only will be the discharge of the ESD buildup. So we once we mitigate the initial buildup, the discharge will become harmless. So whenever a person is trying to enter into an area, for example, electrician or another person into the area where ESD is high, he shall have a intermediate space where he can get discharged. So these are depending upon the site and the area where ESD is generated have to be investigated.
No, I agree, sir. Now
Example,
the my
it can
yeah.
be, for example, it can be a rolling insulating spheres in the
Okay.
process, which can
Okay.
Sir,
generate ESD. There
can I
you
can
can
I add an
directly discharge by
Okay.
applying
can I add an
insulating
answer?
agent.
Sir, can I add an answer?
Hello,
Mr.
can I?
The question of
Hello,
Mr. Davis is
Yeah. It's from yeah,
Davis
Mr.
is if
Gopkumar, sir. Thank you. Thank you for having you.
if
uh,
somebody goes for a electrical maintenance, how does he is protected because he is there without his proper PPEs? So Mr.
That's the
Davis
question.
may I answer to this?
one
Hello,
moment, please. One
yeah,
moment, please. In such location, we are supposed to make a protective measure, fault protective measure called as earth-free equipotential bonding. You can find these rules in IS 3043 as well as IS 732. So the person who is, even though he is working there, he don't get a shock. It's like an IT system, but there are
Okay.
several rules applicable. Thank you.
Okay. Thank you.
So somebody else, Mr. Bodhisattva.
Bodhisattva, yes.
this is Bodhisattva. Hello,
Yes, please go ahead.
am I audible? Yeah. It was a wonderful discussion. I would just like to add a little bit that whenever these ESD discharge wristband or these shoes are used, they mandatorily have a high resistance in the order of megohms connected to the uh, link. So it is not directly wired link. So even if I touch something, let's say I touch a 415 volt supply line with a 230 volt against the ground, what will happen is this will be connected through this megohms level of resistance. So I will never get it electrocuted. It is very important that if I just directly connect myself to the ground, I'll be ready for any electrocution. So to prevent that, all these wristbands or shoes, they have a megom level of insulation in that, which is a highly insulated, but there is a conduction path of 1 megohms. So since these voltages are in the tune of several kilovolts, such a discharge path is very good enough for discharging those high voltages. But any real electrical shock hazard, which is posed by these 230 volts or 415 volt lines, that will not have a appreciable current through this because of this 1 megohm wiring. Sorry. Any wristband, if we take and use a multimeter, we can see that the wrist point and the clip, crocodile clip or the ground strip under the shoe, if I measure between this, we will get a 1 megohm resistor. This is there always. So this
Thank
protects
you.
the person. It was a very good point out that how this person is protected if he is grounded. It is something like he is made to ground connection. It is actually there is a safety because of this 1 megohm. This 1 megohm isolation provides sufficient conduction for high voltages in the tune of ESD voltages and provides sufficient insulation for any real life physical supply voltages. So I hope,
Thank you.
Mr. David, this
Yeah.
is.
Thank you for
So,
clarifying. Thank you.
one very important thing is, sir, anybody who is working with it, kindly ensure that you measure that this resistance is existing. It takes less than a minute to take a multimeter and measure this resistance, but it can actually save your equipment because it may so happen that that resistor has cut off because of some mechanical stress or something, and we are having terrible faith on that strip, earth strip laga liya, everything must be okay. But kindly ensure every day, if you are working with any such setup, you should ensure that this conduction is there, which is having a resistance of around 1 megavolts.
I think, Mr. Bodhisattva, we can continue the discussion offline because we still
Yeah.
have, say, 87
No, that's all.
participants.
That's all. No,
But,
no, no. This is
yeah.
what the only point was, this that this is not an open circuit, and this is a high resistance conduction. Okay.
Okay. Yeah.
Thank you so much.
Thank you so much.
Okay.
Okay.
Thank you.
Over to you,
Thank you.
Anandu, for any closing remarks.
There's no, we got more remarks on the ESD than the telecommunication bonding networks. That is the closing remark. And as Apav sir said, EMI EMC, when you're for a telecommunication, whatever I talked right now, it is primarily for conducted EMI EMC and for radiated EMI EMC. So it differs both. And if you're going for radiated EMI EMC, you have to follow a few more standards such as shielding, which is not covered in today's presentation. Yes. And thank you everybody for attending this program. It was, I think it was a good program with very good responses and interactive answers with respect to ESD.
Yeah. All right. Thank you so much, everybody. We will be closing for now. And actually, hold on. Actually, we have some questions. Although I'm in the chat. Sir, when we connect neutral with protective earth, that time if load is generated, harmonic current that time functional earth also affect and create problem. I don't know. Anandu, is this a question relevant or not?
No, basically with protective earth and functional earth, yes, you will have a single point connection between your functional earth and your protective earth. So you will not face any harmonic issues in your protective earth.
Yeah, because that's the whole point. You only connect it at one point. That's it.
Yes.
Yeah.
And one more point is, it is best if you have everything as a balanced load, not
Hmm.
unbalanced loads and stuff.
Yeah. All right. Thanks so much, Anandu. Thank you, everybody. We will be closing up for today. And yeah, I think there is only one thing. I think, Mr. Gopakumar, we have a mega program in Delhi in happening. So, would you like to brief the participants on it? Because I saw that there's something on the chat about it.
Yes, Krish. Now, for the balance, remaining participants, uh, good afternoon to everybody. We are having NFE is organizing a mega program on 26th June. That is in 2 weeks. Not exactly 2 weeks, less than 2 weeks. The program is a national celebration of National Electrical Safety Day by Central Electricity Authority. So NFE is hosting the program. We will have we are going to launch a big program of skill development of 250 engineering colleges and electrical safety awareness for 2,500 schools. So the program will be launched officially by CEA and the BIS in that particular venue. In the afternoon, we are also having a mega program on how to prevent electrical fires in hospitals. A lot of dignitaries and government officials are expected to participate in this program. If anybody is willing, please look at our social media pages. You can register for the program and please attend. Thank you very much, Krish.